Okay, as discussed in the end of the previous video, we now need to talk about some terminology, and there's a lot of it. So we're going to go over a lot of it in this video, a lot of the basic terminology in graph theory. To begin with, we started out in the previous video and talked about how in a graph, these are called the vertices or nodes of the graph. And then these lines between the vertices are usually called edges. And this is an example of an undirected graph because there's no arrows on these edges. Sometimes you'll have edges with arrows, and then that is a directed graph. Okay, so here's an illustration of a graph. We've called this graph G. And a graph is this collection of vertices and edges, and so we're going to label these as belonging to two non-empty sets. So the vertices, we're going to have the vertices of G, and it's going to equal the set containing V1, V2, V3, V4, V5, and V6, because all of these vertices belong to the graph G. Similarly, we're going to have a set of edges of G, and this is going to have E1, E2, E3, E4, and E5. Now, edges aren't always labeled as they are in this case, so if they're not labeled, what you would do is you would have a set. So instead of writing E1, I would have V1, V2, the pair. And then for E2, I would say V2, V3, and so on. Okay, I'm not going to finish that, obviously, because we were out of space. Okay, but what we do is we define this graph by these two sets, vertices and edges. Now, looking at this graph, this is what's called a disconnected graph, right? Because we can have these what are called connected components. This is a connected component of the graph, but the entire graph as itself is not connected. This is called a loop, and that is where you have an edge from a vertex back to itself. Here, even though they really don't look it, this is what's called parallel edges. And the reason we can say that, we call it parallels because they both start and end at the same vertices. So both the endpoints of both of those edges are the same. Now, in graph theory, where we draw the edges doesn't really matter, right? So this is the same as if we had drawn V4 and V5. We could have drawn it like that, and those are still the same edges. This would still be E4 and E5 because the geometry of it no longer matters. It's now just what are the endpoints and how are they connected. Okay, so those are called parallel edges. This one is called an isolated vertex. Let's do it this way. Okay, as I briefly mentioned in the previous slide, the edges, we can define them by their endpoints. So each edge has either one or two endpoints. Right, so this edge right here, E1, has two endpoints, V1 and V2, and edge 3 down here just has one endpoint, and that's V3. We say that the edge is incident to its endpoints. Right, and so this is a term that you do need to know. It's incident to its endpoints. And the way we can represent these edges, we say that the correspondence from each edge to its endpoint is called the edge, it's really exciting, the edge endpoint function. Okay. So an example of this edge endpoint function is we can say given edge E1 as input, I get the outputs out. Now, my outputs are going to be V1 and V2. Now, it's very important that I'm using these curly braces here instead of parentheses. And that is because as an undirected graph, the order of the endpoints doesn't matter. And we illustrate that using curly braces. When we have directed graphs, we use parentheses because then that order does matter. So it is not interchangeable. You need to be aware of how you are defining this set of endpoints. Okay, E2 is going to be V2 to V3. E3. Now E3 is a loop, and in set notation, we never duplicate elements in a set, so we just have V3 because this is undirected. It's different when it's directed. E4, we're going to have V4 and V5. And E5 is also going to be V4 and V5. And again, because this is the same right here, that's another way we know that those are parallel edges. For vertices, we're going to say that two vertices connected by an edge are adjacent to one another. Okay, and again, just like incident on this page where the edge is incident to its endpoints, we say two vertices are adjacent to one another via an edge. And the endpoint of a loop is then called self-adjacent. Okay, so these are two of the terms you need to know about vertices. Okay, in addition to representing a graph via its edge endpoint function, that's one way to represent a graph, you may wonder, how, if I was programming something about graphs, how would I do it? Well, the edge endpoint function does work, and you can create such a function and follow through, but it's going to be difficult to see what all the connections are. So a common and simple way this is done is called an adjacency matrix. And in an adjacency matrix, I'm going to start with a vertex. So let's start with V1. And I'm going to say, well, what is V1 attached to? Now notice we're doing an undirected graph here, and that is going to be important. So V1 is attached to V2. Is it attached to V1 at all? No. So we're going to put a 0 in that spot. It is attached to V2 though, so I'm going to put a 1 in that spot. And notice that's the same as saying that V2 is attached to V1, so there's also a 1 in this spot, right? So this is sort of where we're starting and where we end up. But because this is an undirected graph, it's going to be symmetrical. Okay, so let's just start at V1. V1 is not connected to anything else, so we're going to have zeros here. V2 is connected to V1. It's also connected to V3. And zeros everywhere else. V3 is connected to V2 and itself. V4 is only connected to V5. And V5 is only connected to V4. V6 has not connected to anything. Okay, so right here, this is an adjacency matrix that represents this graph. And because it's undirected, it's going to be symmetrical over the diagonal. So notice that we have the 1, 1, 1, 1, 1, 1. This, because it's on the diagonal, it means it's going to be a self-loop. Right? But, so this is the adjacency matrix for an undirected graph. Okay, we're almost done with terminology now. We're going to look at an adjacency matrix for a directed graph. This is the same idea, except now order matters. So notice V1 does not have any edges leaving it, so it's going to be zeros all across. V2 attaches to V1 and V3. V3 attaches only to itself. And we can put all these zeros in. Sometimes people just leave the zeros out for ease of viewing. So that would look like this. V3 is only connected to itself. V4 is connected to V5 twice. All right, so we're actually going to have a 2 here. V5 isn't connected to anything, and neither is V6. So I find it a little easier to read this with the zeros in place. But notice this is no longer symmetric. And that is, again, because we have a directed graph. And the last term that I want to talk about in this video is something called a subgraph. We say H is a subgraph of G if and only if the vertices of H are a subset of the vertices of G, and the edges of H are a subset of the edges of G, where the endpoints are the same. Okay, so we have a graph G here, and we can construct a subgraph. I'm just going to draw it in red right here. Right, so this is a subset of G, and we could redraw it. We could have this as vertex 7 and 2, 3, 5, and 6. Right, and this is going to be a subset. We can say that H is a subgraph. Let's do it over here. We can say H is a subgraph of G in this scenario, because again, our vertices are chosen as a subset of G's vertices, and our edges are a subset of G's edges. And we can't just add like a random edge. Like we couldn't just have this edge going to 4, for example, if we don't have 4. But other than that, this should be pretty straightforward subgraph. So in the next video, we're going to see kind of an interesting application of graph theory.